Okay, for number 19, we are looking at a rectangular piece of cardboard. And we want to cut square pieces out of that cardboard. We're going to cut square pieces out of the corners. So we're going to call each one of these X. Okay, and of course that's X for each part of the square. Okay, so I'll draw a little picture there to help us kind of visualize this. And the cardboard was originally 12 inches long. That from here to here is 12 inches. There we go. And the width was originally 10 inches wide. So here's the width, and here's the original length of that rectangular piece of cardboard. We want to actually think about in terms of the box. So if we cut these squares out and we fold up the box, we want to know what is the new width, which would be here, and what is the new length of that box. And remember that the picture now that we're trying to visualize here is if we cut out those squares and we actually draw this open box. So it would look something like this. Alright, so the height of the box, of course, would be the x. So we're going to say the height of the box is x. The width of the box, then, since we cut off those x values at each corner, the new width of the box will be represented by 10 minus those two x values that are gone. And the new length of the box will be 12 inches, take away those two x corners that are gone. So we have the new length of our box, and then we have the new width of our box. Keep in mind that we talked about, we wanted to make sure that all of these are positive values. So the height, which is x, and the width, which is 10 minus 2x, and the length of the box, all of these distances have to be greater than or equal to 0. So we want to make sure that we are bounded by the x values that will cause that to happen. So let's spend a little bit of time coming up with that. So the minimum value that x can be here, we see that x has to be at least 0. So we have that. Let's solve for the width as well. So 10 minus 2x has to be greater than or equal to 0. So we're going to subtract 10 from both sides. Divide by -2, and we end up having to flip our inequality symbol. So we get x is less than 5. So we'll keep this in mind, and let's go on to the next one. The length says that 12 minus 2x has to be greater than or equal to 0. So we'll subtract 12 from both sides and then divide by -2. Flip our inequality symbol, and this says that x has to be less than 6. Remember that we want to go with the most exclusive value. We want to go with the upper bound that works for both. Okay, so if we think about this as a number line, x equals 0 is the starting value, and then we have 5, and then we also have 6. So for the width to be happy, we have to choose a value in between 0 and 5. So 6 will not work to keep the width happy. Okay, so we're not going to use all the way to 6. We're going to choose the upper bound to be 5. And if the upper bound is 5, then these values will remain positive, and then also the values for the length will also remain positive. So we're going to go with the most exclusive. Okay, so the upper bound for our x will be 5. Okay, so here's our bound for x. This is what our function will have to, the x values will have to come from in order to keep all those distances positive. So let's go back up here and look what we were asked to find. So we have the picture, and we're going to have all of our bounds. We were asked to find the dimensions of the box that will yield the maximum volume. So we want to maximize the volume. And remember that volume is length times width times height. And you can write those in any way that you wish. So we're going to say the volume is equal to the length times the width times the height. And I'm going to write this as the height just because it's more convenient, times width times length. It doesn't matter the order. So we're going to maximize. Let's call this v of x. We'll write in function form. And the height of the box is x. The width of the box is 10 minus 2x. And the length of the box is 12 minus 2x. And remember that we have our bounds, our upper and lower bounds for what x can be to keep those values positive. Okay, we're going to rewrite this function. I'm going to go ahead and multiply in the x, so that gives me 10x minus 2x squared. And I'm going to multiply by 12 minus 2x, and we're going to FOIL here. Okay, and when I FOIL, I end up getting 120x minus 24x squared minus 20x plus 4x cubed. I'm going to combine like terms, and I'm also going to rewrite it in a way that is a little bit nicer with the highest exponent first. And I'm going to include my bounds again. So this is what we're going to be working with for the rest of the problem. Since we want to maximize the volume, we want to first take the derivative of that volume function. So that'll give us 12x squared minus 88x plus 120. And we're going to set this equal to 0. And we're going to solve for x. Now this particular equation will not factor, but one thing I want to do is go ahead and divide out by the common divisor, so they're all divisible by 4. So let's go ahead and do that. We'll do that to both sides of our equation. And we end up getting something a little bit simpler. We end up getting 3x squared minus 22x plus 30 is equal to 0 divided by 4, which is 0. Okay, so we're going to set this equal to 0 and solve for x. And this does not factor. And if something doesn't factor, then we'll have to use the quadratic formula. Okay, so we have x is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, so let's simplify a little bit there. We end up getting x is equal to 22 plus or minus the square root of 124 divided by 6. And we'll go ahead and take the square root of 124, we'll round to the nearest 2 decimal places there, so that would be 11.14 divided by 6. We separate with the plus and the minus, and we end up getting 2 x values. We end up getting 5.52 for one of them, and then for the other one we ended up getting 1.18. And let's look at these x values and see if they're even in our domain. So remember that the bounds for our function were in between 0 and 5. If we choose anything outside of those bounds, then one of our distances, one of our dimensions turns out to be negative. So 5.52 is out of the boundary. So out of the bounds. So we're going to go with 1.81. Alright, so we're going to plug this into the original function. So the original volume function, we're going to test out for 0. And if you plug in 0, you get 0, which is kind of nice. If we plug in 5, we also get 0. So we plug in the endpoints, we get 0. When we plug in the value that we found for x, 1.81, and we're going to plug that into our function, remember the original volume function there. Okay, Okay, put that in your calculator exactly as you see it, and you end up getting 96.77. Now we're talking about volume, and in the problem we had inches, so inches cubed. So the maximum volume will be 96.77 inches, and we want to know what the dimensions are for the height and the length and the width. So the height, of course, the x value that we had was represented by the height, and that's 1.81 inches. What would the width be? Well, the width was given to us as 10 minus 2x, so that would be 10 minus 2 times 1.81. Put that in your calculator as is, and we end up getting 6.38 inches. And then the length was 12 minus 2 times x. We'll put that x value in, and we end up getting 8.38 inches. So these would be the dimensions of the box to obtain the maximum volume of 96.77 cubic inches.